Welcome to homework.
We can determine the radius of the wire using equation 12.5, where we have a relation between stress and strain. So we have F over A, which is stress, is equal to elastic modulus times strain, which is equal to del L over L naught. From here, we get area to be equal to F times L naught over E del L. And we know that area is pi r square for the cable, where r is the radius of the cable. So r will be equal to square root of Fl naught over pi times E times del L. And let's keep it inside a box. And let's call it equation 1. We will use it later after we have found the force F, which is Ft here. And yeah, now let's find the tension force using from this free body diagram for the point of connection of the mass to the wire using Newton's second law. For equilibrium, the net force along y direction should be equal to 0. And here we have two forces, Ft sine theta going up for each of these sections. Then we have mg going downward. And this is equal to 0. So from here we can find Ft, which is equal to mg over 2 sine theta. And let me just write the values of the masses and theta that's given. So we have m equal to 25 kgs, g is gravity, and theta is given to be 12 degree. So we use these values over here and find Ft to be equal to 589.2 Newton. And remember that Ft is the tension force and is the same force that we will be using over here. Or we can say Ft is the stress force. Now the fractional change in the length of the wire, del L, can be found by finding cos theta, which will now, so basically I am using this diagram now. So cos theta will be equal to L naught over 2, which is the base, over the hypotenuse, which is equal to L naught over del L over 2. And this figure is basically half of the section of this system, this whole figure. So basically, this is the section that's drawn here after stretch. And since the length is changed by del L, so each of these segments will change by a factor of del L over 2. And yeah, that's what we should add to the initial length. From here we can find del L, which will be equal to L naught times 1 over cos theta minus 1. And this gives a ratio, since we don't know L naught, let me just find the ratio of del L over L naught. And that comes out to be equal to 1 over cos theta minus 1. And if you plug the value of theta, which is given to be 12 degree over here, we find the strain to be equal to 2.234 times 10 to the power minus 2. And this value, the strain, is what we will be using in this part. Now let's go back to equation 1. So what we got, R to be equal to Ft L over pi E del L. So Ft, we can write, there's a root over, so now this can be written as Ft times 1 over pi E times 1 over del L by L, basically this part. Now elastic modulus for the cable is 70 times 10 to the power 9 Newton per meter square, and this is the value that we will use here, including the value of Ft and strain that we just calculated, and plugging that and solving for R gives us 3.5 times 10 to the power minus 4 meter. So this is the radius of the cable.